Hello friends, in the previous lecture we have discussed about the introduction part of the soil mechanics. In this lecture you are going to learn the basic properties of the soil mechanics and their relationships. See, soil, if you see soil material outside, so how it looks like. So if you take some part of soil, if you take some sample of soil, in that soil there will be solid particles, and there will be water, so all these are solids. This is water, this is water, and the rest of the portion maybe it is occupied by air. So soil is a combination of solid, air and water. Okay. So if you want to represent this soil in the form of a phase diagram, for our better understanding, what we do generally, we draw them in the form of a phase diagram. Phase diagram is nothing but phase diagram of soil. See, phase diagram is nothing but, for example, I will take a small cylinder. Okay. Now I will bring all the solids. And drop in the cylinder Then this much volume is occupied by these solids. So this is the volume of solids or soil particles. We can say this as soil particles. So volume of solids, or we can say it as soil particles. Now whatever the water is present in this, okay. So now whatever the water present in this, I will put this into the jar. Then this is the volume of water in it. Okay. Volume of water. Now if I take the same soil into a jar, okay, for example, the same soil without differentiating the solids and water, I have taken this soil completely in a jar. So now I have taken this soil completely in a jar without bifurcating water, solids and all. So now I got the total volume as V. So if this is Vs, this is Vw, this should be what? Volume of air only. So soil may have solid, water and air. So if this is the total volume, for example, if this is the total volume, let us say, if this is the total volume of soil, so if you exclude solids and water, whatever the volume which is left is nothing but volume of air. This is nothing but volume of air. So if I close it, so this is the phase diagram. So for our easiness of calculation, we use this phase diagram. So now this is solids, this is water and this is air. So this is the phase diagram. So these are the volumes. Similarly, the solids will have some weight. This is weight of solids. The water will have some weight. This is weight of water. The air will have some weight. This is weight of air. Generally we take the weight of air as 0, because what is the weight of air? Does the air gets weight? Air won't have any kind of weight. So that is why we can assume it as 0. So these are the volumes and these are the weights. Now relationships mean these are the properties. These are the different properties. And using this we can derive some secondary properties. Let us see what are the secondary properties. Before moving on to this, we need to understand this is a phase diagram which is showing 3 phases in it. which is showing three phases. What are the three phases? Solid, water and air. That means solid, liquid and gas. So there will be two-phase diagram also. This is the three-phase diagram of soil. This is the three-phase diagram of soil. This is three-phase diagram of soil. There will be two-phase diagram also. There will be two-phase diagram also. Two-phase means two-phase. For example, if the soil is completely saturated. So if the soil is completely saturated. So for a saturated soil, saturation means what? Saturation means all the air voids are occupied by water. All the air voids are occupied by water. That is nothing but saturation condition. So saturated means, so there won't be any air void. Now the water will take till the top. Total voids. See here, this is the voids. Here if you see this, so this is the volume of voids. Here volume of the void. This volume of voids are taken, some voids are taken by water, some voids are taken by air. So if there is no air, so completely the voids are filled with water, then we call that soil as the saturated soil. For a saturated soil, the phase diagram will be like this. The phase diagram for a saturated soil will be like this. So there will be only solids and water. Okay, here the volume of voids is equal to volume of water, and here this is volume of solids, and here it is weight of solids and the weight of water. Here this is weight of water. So this is a two-phase diagram. This is a two-phase diagram in which you are only having water and solids. We are having only water and solids. Okay. So similarly, for a dry soil, dry soil means, so there won't be any water now. Now the same two-phase diagram, instead of water there will be air. Instead of water there will be air. So this is volume of voids, which is equal to volume of air, and this is equal to volume of solids, and this is weight of solids, and here weight of air, which is negligible. So these two are the two-phase diagrams. Now tell me, will water will have the four-phase diagram? Does water have four-phase diagram? Please think and tell. Does water have four-phase diagram? Does water have four-phase diagram? I will say yes. Because if the water is also containing ice, if the soil is also containing ice also, okay, then we will be having four-phase diagram. So four-phase diagram is possible only when the soil contains solids, liquid, water and solid water, that means ice and air. See, 1, 2, 3, 4, that is four-phase diagram. See here, solid, water, ice and air, water, ice, solids. So this is four-phase diagram. It is also possible. We can also say that four-phase diagram is also possible, provided that the water is also containing some amount of ice in it. So these are the phase diagrams. Now, using these phase diagrams, we will derive some properties of the soil. Let us see what are the properties we are going to derive. See, first one is the void ratio. So what is meant by void ratio? Void ratio is nothing but void ratio. Void ratio is indicated by a small letter E. Void ratio is indicated by small letter E, and its formula is volume of voids by volume of solids. Volume of voids by volume of solids. If you see the phase diagram, okay, so this is solids, this is voids. Okay, this is solids and this is voids and solids. Now, so volume of void by volume of solid, it is nothing but void ratio. Okay, or else we can write it as into 100 also. If you want to represent it in percentage, you need to multiply it with 100. Now here, what is the other thing we need to understand is, what is the limits of this void ratio? What are the limits? Generally, see the limit, generally E is greater than 0, because can void ratio become 0? Can void ratio become 0? Is there any soil in which the void ratio is 0? No. Practically it is not possible. It's a hypothetical. So it's a fictitious soil. There is a fictitious soil which is in our assumption, which is having 0 voids. But in practicality, in reality, it does not exist. So volume of void cannot become 0. It is impossible for us to make it 0. So it cannot take 0 value. So E cannot become 0. Now, can volume of void equal to volume of solid? Is it possible? If volume of void is equal to volume of solid, then where is solids? Without solids, how can you say that it is a soil? So for calling it as a soil, we need solids. So when there is a little amount of solid, then void cannot be equal to soil volume of soil. Okay, volume of soil, it cannot be equal to volume of soil. Okay, this is volume of soil. It cannot be equal to volume of soil. Now it can take any value. That means if the void ratio can be greater than volume of solids, it can be less than volume of solids. Okay, it can be greater than volume of solids, it can be less than volume of solids. If it is greater than volume of solid, then VV by Vs is greater than 1. That means E is greater than 1. So E is greater than 1 means it has no upper limit. E has no upper limit. So that is why it can take any value greater than 0. It can take any value greater than 0. Here, for defining E, generally for different soils, we will be having different void ratios. For example, see, there are different types of soils: gravel, sand, silt and clay. So we will be having different sizes in it. If you see the size, so size of gravel, so gravel size is greater than sand size, is greater than silt size, is greater than clay size. Now what is the pattern of void ratio now? So if the size of the particles are increasing, then what happens to void ratio? Will it increase? No. See, if the void ratio, if you see, void ratio of gravel will be less than void ratio of sand, and it is less than void ratio of silt, and it is less than void ratio of clay. Because when the size of the particle increases, okay, when the size of the particle increases, size of the void increases. Okay, when the size of the particle increases, size of the void increases. Size of the void increases. But volume of the void decreases. Volume of the void decreases. Why? I will show it pictorially. See, now here in the same vessel, I will take clay particle and I will take gravel particle. See, this is gravel. This is gravel. Okay. I am taking gravel in this, so I am taking clay in this, so I am taking clay in this. See here, the clay particles are having very less size, so number of voids, if you see the number of voids will be more here. So though the volume of each void is less, number of voids is more. Here, though the volume of each void is more, number of voids are less. That is why when the size of the particle increases, size of the void increases, but volume of the void decreases. So larger the particle, lesser will be the volume of void. If the volume of void decreases, obviously void ratio decreases. If the volume of void increases, obviously the volume of void ratio increases. So that is why gravel void ratio, sand void ratio, generally gravel will have a maximum void ratio of 0.91. Maximum void ratio of 0.91. See how it is 0.91. See how it is 0.91. How the gravel is having 0.91 maximum void ratio. Whereas if you see clay, it may have a void ratio more than 1, more than 2. Sometimes if it is having montmorillonate in it, it may have a void ratio of 2.63 also sometimes. Okay, so that means depending on the clay mineral also the void ratio varies. So for a clayey particle the void ratio may be in a range of 2-3 also, but whereas the gravel is having a maximum void ratio of 0.91. How? Let us see. How? Let us see. Now, for example, I will take a cube like this. I will take a cube like this. Okay, so this is a cube of unit dimension. So length, so I will take all the dimensions as unit. I will take all the dimensions as unit. So this is 1 meter, 1 meter and 1 meter. Length, width and height all are 1 meter. In this there are gravel particles uniformly sized. For ideally I am taking a gravel as a form of a sphere and it is having a uniform size and uniform shape. Now here this is total volume of the soil. If you take the total volume of soil, total volume of soil is equal to volume of the cube. Volume of cube, that is equal to how much? 1 meter cube, isn't it? Total volume is nothing but what? Volume of soil is nothing but volume of solids plus volume of voids. So here in this there is a volume of solid and there is void, there is solid, both are there. So the total volume of this cube is nothing but the volume of the soil. So that is 1 meter cube. Now size, volume of the solid, volume of solid is equal to number of solids into volume of each solid. Volume of each solid. So volume of solid is equal to number of solids into volume of each solid. See, for example, the diameter of this is D. I assume that the diameter is D. For this particle, diameter is D. Now, how many particles I am having now? How many particles? If it is 1, this is 1 meter. This is diameter D. Okay, so this is diameter D. And this is 1 meter. Let us assume that there are n number of particles. Let us assume that there are number of solids is equal to n. Let us assume that number of solids is n. Number of solids is n. So if number of solids in 1 meter length is n, then diameter of each solid is equal to how much? 1 by n, isn't it? If there are n particles, 1, 2, 3, 4, 5 particles are there. For example, there are 5 particles. All are having same dimension, the same diameter. Then what is the diameter of each particle? 1 by 5. Similarly, if there are n particles, then the diameter of each particle should be 1 by n. Now volume of each particle, volume of each particle is equal to 4 by 3 pi r cube. So I am assuming them as spheres. Now sphere, this is the volume. So each particle volume will be 5 pi into what is r? This is diameter. That implies r is equal to 1 by 2n. R is equal to 1 by 2n. So 1 by 2n whole cube. That means 4 pi by 8. So 8 into 3, 24 n cube. So this is pi by 6 n cube. So volume of each particle is equal to how much? Pi by 6 n cube. Pi by 6 n cube. Okay, so total volume of solids. Total volume of solids is how much? Number of solids into volume of each solid. So what are the number of solids now? So in this line there are n. Similarly in this line there are n. Okay, similarly here also, this is also unit na. If there are n particles here, there will be n particles here also. There will be n particles in this dimension also. In this dimension also you are having. So this is n. Okay, this is n and this is also n. This is also n. So n, n, n. So lengthwise n, widthwise n, depthwise n. So total number of solids is multiplication of this. So total number of solids here I will write like this, n per unit length, because I am taking like this only, n per unit length. Okay, n per unit length. So total number of solids is equal to n cube, n into n into n cube. So volume of solid is equal to volume of solids, so number of solids, that is n cube, into volume of each solid, that is pi by 6 n cube. So it will get n cube get cancelled, so it is equal to pi by 6. So volume of solids is pi by 6. Volume of soil is, this is the total volume. So total volume of soil is 1 meter cube. So volume of soil is nothing but volume of solids plus volume of voids. Volume of soil is nothing but, so volume of soil is nothing but volume of solids plus volume of voids. See in the phase diagram, this is solids, this is voids. So this is volume of voids, this is volume of solids. So the total volume of the soil is nothing but volume of void plus volume of solid. So this is fixed. So total volume of soil is equal to volume of solids plus volume of voids. So you know the volume of solids, how much? Pi by 6. Okay, you don't know volume of voids, but you know the total volume of soil. Total volume of soil is 1 meter cube. Okay, so that means volume of voids is equal to 1 minus pi by 6. So this is volume of voids, 1 minus pi by 6. Now void ratio is equal to volume of voids by volume of solids. That means 1 minus pi by 6 by 1 minus pi by 6 by pi by 6. If you do this, you will get 0.91. If you do this, you will get 0.91. That means this is the way how we determine the maximum void ratio of a uniformly grained gravel or any kind of coarse grained soil. So in a coarse grained soil, the maximum void ratio, this is the maximum void ratio. E max is equal to 0.91. Okay, similarly in the same cube, okay, in the same cube, generally if I arrange it in a pattern, in in a specific pattern, then I will get the void sizes, volume of voids get reduced. How I will show? For example, if I am arranging like this, okay, so with some angle, see, earlier I was keeping the next one exactly on the top, but now in the modified arrangement I don't keep it like that. I won't keep it like that. I will keep it here. I will keep it with some volume, with some inclination. Okay, see, with some inclination. Similarly, I am keeping it with some inclination so that the void sizes can be reduced. So now it will take a different shape. It will take a different shape. Earlier it was like this. See, it is taking a shape which is lesser than the earlier one. Earlier this was the cube. So now it is taking lesser volume. So the volume of soil decreases, volume of void decreases. So this is nothing but diagonal arrangement. Diagonal arrangement. If you put it in a diagonal arrangement, if you put the soil particles in a diagonal arrangement, then we will get the E minimum. So E minimum will be 0.34. E minimum, if you are keeping it in a diagonal form of arrangement, then you will get the E minimum, that is 0.34. So the minimum possible void ratio in a coarse grained soil is 0.34, and in a fine maximum void ratio in a coarse grained soil is 0.91. So these two values are important. Okay, now moving on to the next property, that is porosity. This is all about void ratio. Next is porosity. So what is meant by porosity? Porosity is nothing but the ratio of volume of voids. Porosity is nothing but the ratio of volume of voids by total volume of soil. Volume of voids by total volume of soil. So volume of voids, or else I will write volume of voids by volume of soil. Now if you see this in the form of a phase diagram, so this is a phase diagram of this. So this is Vs, this is Vv, and this is total volume V. So Vv cannot be become 0. So Vv will not equal to 0. Okay, practically. Practically Vv cannot become 0. It is not possible to make voids 0. So Vv never takes a value 0. So if Vv never takes a 0, then n is always greater than 0. Okay, Vv is always greater than 0, but it will not equal to 0. Now what is the maximum value of Vv? For example, if Vv is equal to Vs, okay, or else Vv is equal to V, that means Vs is equal to 0. Okay, if Vv is equal to V, that is Vs is equal to 0. Is it possible really? Without the solids, can we say that it is a soil? Without solid particles, can we say that is a soil? No. So it is not possible. So Vs is equal to 0 is not possible at all. So Vv cannot become V. Vv in any condition cannot equal to V. That means the maximum value, if Vv is equal to V, then n is equal to 1. But Vv cannot become V, that means n cannot become 1. So the maximum value of n is always less than 1. The maximum value of n is always less than 1. So likewise, if I am putting it here with 100, so if I am taking it as a percentage, then I can write it as 0 n less than or equal to 100%. So these limits are important for gate. The limits are very important for gate. Limits, how we specify the limits? By simply putting the value. So VV 0 is not possible. So VV cannot, n cannot become 0. VV is equal to 0 is not at all possible. That is why n will not take the value 0 at any time. And VV cannot become V, because if VV is equal to V, if it becomes equal to the volume of soil, then volume of solid should become 0, which is not possible. So that is why VV cannot become V, that means n cannot become 1. So always it ranges between 0 to 1. So, or if you are taking it as a percentage, then it is 0 to 100%. So these are the limits of porosity. This is porosity. Okay. Next is degree of saturation. Degree of saturation. Next is degree of saturation. Degree of saturation. See, whatever the notations I am representing is my notations. In different textbooks there are different notations. In some textbooks they notate it as S, but I am notating it as SR. It is my notation. Okay, you can change your notation as per your convenience. Okay, so degree of saturation is nothing but volume of water by volume of voids into 100. Volume of water by volume of voids into 100. That means if you see the phase diagram, so this is volume of water, this is volume of voids, this is volume of voids. So what is the amount of water present in the total voids? What is the amount of water present in the total voids? That is the degree of saturation. Degree of saturation. See, this VW, if there is no water at all, for dry soils, this VW will become 0. This VW will become 0. That means SR becomes 0. For saturated soils, this VW will become, it will completely occupy all the voids. Okay, when it is a saturated one, this VW will completely occupy the total volume of the void. In that case, saturation will be 1. So because VW is equal to VV, when it is completely occupied, VW, VV, both are equal. That means it should be 1 or 100%. Okay, so where for dry soils, where VW is equal to 0, okay, VW is equal to 0, then SR is equal to 0%. Okay, for fully saturated soils, VW is equal to VV, then SR is equal to 1 or 100%. SR is equal to 1 or 100%. So the limits of SR, 0 less than or equal to SR less than or equal to 1 or 100%. So this is the limit of degree of saturation. This is the limit of degree of saturation. So further formulas, we are further properties, what are the properties we are having, we will discuss this in the next class. Okay, thank you.